Today, artificial intelligence is steering fleets of autonomous vehicles through complex urban traffic and generating intricate text on command. While these applications are diverse, they almost all run on a single, unified computing infrastructure built by one company. The company's story began in the early 90s, during the first major expansion of the personal computer market. CEO Jensen Huang co-founded the firm with a specific goal: developing specialized hardware to render 3D graphics for PC gaming. The mathematical work required to draw light and geometry in these games relied on a very specific type of high-speed calculation, a method that would eventually find a second home in scientific research. Creating fluid motion in an early video game required calculating the exact color and position of thousands of individual pixels simultaneously. To manage this workload, they developed the Graphics Processing Unit, or GPU. A standard CPU acts like a single high-speed pipe processing tasks sequentially. In contrast, a GPU uses thousands of smaller parallel pipelines. Researchers discovered these parallel pipelines could process abstract scientific datasets just as effectively as they rendered visual pixels. The company then released CUDA, a software platform that allowed developers to program GPUs for general-purpose computing. This move turned the company from a manufacturer of consumer electronics into a provider of scientific supercomputing power. The business has evolved beyond selling individual chips to building what they call AI factories. This ecosystem starts with foundational silicon, Hopper, Blackwell, and Vera CPUs. Next are physical DGX servers and networking cables linking thousands of GPUs into a single cluster. Finally, software APIs and AI models like NIM and NeMo allow developers to deploy applications. Because these software tools are built specifically for the underlying chips, enterprise companies often find it more efficient to stay within this integrated ecosystem. Controlling every layer from the silicon to the software gives the company a significant advantage in the AI infrastructure market. This chart shows the result, a steep climb in market valuation that recently crossed the $1 trillion mark. The company acts as the primary utility for the industry, providing the high-bandwidth hardware that almost every major AI developer currently depends on. In the automotive sector, companies like Mercedes-Benz and Hyundai use this infrastructure to develop and test autonomous driving functions. In logistics, these same systems power robotic arms that enable zero-touch autonomous manufacturing. The value of this digital ecosystem is measured by its capacity to automate physical movement and real-world supply chains. However, the company faces a growing threat from its own customers, as major tech firms begin designing their own custom chips to reduce their dependence on external suppliers. Relying on a global supply chain for high-end semiconductor fabrication leaves the company vulnerable to disruptions in manufacturing. Geopolitical pressures and export restrictions also limit the company's ability to distribute its most advanced technology globally. Maintaining their lead requires staying several generations ahead of competitors who are now building their own hardware. The next push is into agentic AI, systems designed to reason and execute multi-step tasks autonomously rather than just responding to prompts. This involves using the Omniverse platform to create digital twins, accurate digital replicas of environments used to train robots. By running millions of trials in a simulation, an AI model learns to balance and move before entering a physical machine. From their start in computer graphics, the company has moved into the role of architect for industrial-scale simulation, providing the tools that bridge digital training and physical action.